towards the end of your presentation, and we can do that too.
Good, thank you. Okay. Thank you for a very nice introduction. Well, I would like to thank organizers really for inviting me because it is very exciting to be here. And I would like to thank all of you for the time to be here. And speaking about the time, I think that the timing of this talk is also just about right, because there will be soon coming new release of the SciPy library. And I think that all of you is here because you would like to know about the new developments in the Python world. And SciPy library is one of the projects which is pretty crucial for many data scientists around the world. And we have been hosted, there was a hackathon hosted by AHL, which was very nice. And we were working on implementing the stable laws. There has been already some kind of development done in that area. I am not super exciting about the development which will go into the new release, but partly because I am not excited, it is important before you start to use it to give you a sort of one-on-one stable laws introduction, such that you know what you are going to be facing and what are the troubles you might run into. Because if you learn how to work with that large class of the probability distributions, it is pretty much going to change the possibilities which you have in the modeling world. So, wow, it's great. It says, yeah, okay, hopefully it is going to fit well. Right, so you might be asking, what are the stable laws and how it comes that if they are so important that they haven't been implemented earlier. In a certain way, they are not the celebrity between the probability distributions because they don't have the nicest properties on the planet which people might like in order to use them very efficiently. But they have loads of nice properties, and thanks to the computational power which we have in these days, I think that it is just about right time to really start to work with them. So if I start with some motivation, I'm really quite surprised that it actually doesn't fit properly the slides, but I will be sort of moving it around. So if I start with some motivation, why not to start with a Gaussian distribution, which everyone knows pretty much by heart? It probably wouldn't be necessary to remind you the density of the probability distribution, but just to motivate the talk, maybe this picture might be quite important. Because when you look over here, these are the quantiles. And on this axis, we have basically the range between the quantiles of the probability distribution. So over here, this is the probability of 0.0015. This is this remaining tail over here. And over here, there will be just a very, very tiny probability mass left. So we could basically squeeze majority of the probability mass into this picture. What it means is that in the world where Gaussian law lives, the extreme events are not happening really very often. And pretty much the tails of the distribution decays exponentially. But what if we move to a different world? We will move to the world where things will be a bit more awkward, right? We will have the distribution which doesn't have first finite moments, which doesn't have second finite moments, whose tails will be decaying with the order 2, with the power 2. And if you look at this picture, you will see that not 0.15% of the tail, but 15% of the tail on this picture is missing. And that over here, not this tiny little amount of the mass is missing, but 5% of the mass is missing. And we might consider other example, because there is never enough French mathematician during one talk. So in this case, we have a Levy distribution. And before, at least those first two distributions which I have shown you, these have been symmetric. This guy is not symmetric at all. If you look at this picture, the probability mass of this distribution is located solely on the positive semi-axis. And if you look over here, there is a 30% of the tail missing. and this is the power law with which the tail is decaying. But we are still quite lucky, because we actually still have the density. So we would be asking, like, what has these three distributions in common? Is there something which they have in common? Well, if you would do a little bit of the math and play a little bit with the densities, you could derive this particular property. You could actually figure out that you can scale them. And this scaling property over here, that is that strong property of the stable laws. So if we think about it a little bit differently, because I was saying that they are not very user-friendly. And so those of you who doesn't like complex variable, I have to disappoint you. Complex variable is the best way how to deal with the stable laws. So let's take our densities into the Fourier domain, or let's apply the Fourier transform on them, and let's take it into the complex world. And now you see that there is a bit more visible pattern. But so over here, these guys will be real numbers, and over here there is doing some imaginary number. So we have here some complex number. So that is that particular thing of the characteristic functions, because when the characteristic function is a real, it is the probability distribution would be symmetric, and when the characteristic function has imaginary part, non-trivial, so in that case we have that asymmetry mass of the probability distribution. So we can quite nicely write the probability, the characteristic function like this, and we would basically just want to have the real part bounded, such that we can compute we can invert the Fourier transform, and this is pretty much it. But there might be a question, and the question is, we have seen values 0.5, 1, and 2, but can the parameter alpha take other values than those three numbers? So, I mean, if it couldn't, I wouldn't be standing here. So the answer is very simple. Yes, it can. But there are some boundaries. And the boundaries is that the parameter tends to take values between 0 and 2. And if we are at the level 2, it is the Gaussian distribution, which is the limiting one. And if we are at the level 0, we are strongly bounded from the 0, because otherwise it wouldn't make much sense, and we would be just having pretty much non-random variables. So it would be just a constant. But let's think about the things a little bit more from a different view, because there is a particular thing which people like about the Gaussian distribution, and it is mainly its limiting, the fact that it arises in the central limit theorems. Why would you like central limit theorems? Imagine you are doing loads of experiments. You are collecting your data for your new machine learning algorithm, right? And what would you like to do is that these data are scattered all over. And the basic thing which you tend to do would be feature preprocessing. And you would like to transform your variables. So you would like to move them in a certain way, such that they would be somehow measurably located. You would like to, because they might have different masses, they might be coming from the distributions which are located in a different points. So you try to standardize them. So you try to shift their location, and you would also remove some kind of scales which are in them, such that you can transfer them in the dimensionless units. So the life is very simple if you can compute their first and second moments. But what you would be doing if you can't, like in the case of the Gaussian distribution? So you can find some constants which can help you. It can be mean. It can be median. It can be some truncated variance maybe, or you might be just moving the interquantile size of the distribution. So you can play with all sorts of things. But the question is, what would be the properties? Is there some kind of central limit theorem existing for this kind of problems? So when you think about the simplest convergence of the sums, of the random sums, this is when you are throwing the coin and you are trying to figure out what is going to be the number after a couple of after a couple of toss coins. And it's not really a couple of toss coins, it's a pretty large number of the toss coins, because you would like to go with your toss coins to infinity. So if you just consider a normalized random sums, and you would take the partial sums, and one of the basic central limit theorems will tell you that the random variable to which these sums will be converging will be normal distribution. But there is something a little bit stronger. The basic central limit theorem will tell you that you don't really need to have somehow random variables coming from the same distribution, but they can happily have different variances. They can even have different means. It doesn't matter. What matters here is this condition, which can be reformulated, and you can know it as a Feller condition or whatever. We like these things in mathematics, but I believe not everyone has the same kind of feelings as I do for all sorts of integrals. But the main thing is over here that the tails are well behaved and the tails are very nicely decaying. And if the tails are well behaved and they are decaying, what happens is that we would end up with the normal distribution. But now let me challenge you. What happens if the tails are misbehaving? What happens in the case of Cauchy distribution? Would there be some kind of central limit theorem? How would you handle observations coming from this distribution? There is a good answer. You can handle them, and you can handle them such that the probability distribution to which these observations will be converging, there will exist norming constants and the location shifting constants such that you have in the central limit theorem, the classical central limit theorems. But at the same time, you will be having a limiting distribution, but because the tails are misbehaving, you have the heavy tails and you have the extreme events happening more often than in the nice, well-behaved world. The limiting distribution is really going to be the Gaussian. Sorry, not Gaussian, but the stable non-Gaussian. So, at this moment, it is probably appropriate to say what are the stable distributions more mathematically. So it is all about the sums. So think about the sums which we had. So you have your random number variables, and you want to approximate some kind of event. So you would sum the random variables. What is happening over here is, think about the normal distribution. If you sum up the random variables in the normal distribution, the sum is going to have the same, is going to keep the shape. So it is going to be still a shape-wise Gaussian distribution. It might be shifted in the location, its scale might be different, but the shape remains the same. If you want to think about counterexample, think about what happens if you sum up exponential variables. I think that in that case, the sum is going to have a gamma distribution. So here you see that the property of the stability isn't preserved, but that it is quite precious property, which allows you to relax conditions when you are doing some kind of mathematical modeling. The norming constant, there is a very nice theorem which you can prove, and I think that when I started to work with the stable laws like 10 years ago, I just literally read Feller volume 2, and I think that that's one of the very good books to read in general for the probability theory. You can very nicely prove that the norming constant will look like this. So when you are having your estimates and when you are working with the Gaussian distribution, this is just that square root of n, which you would tend to use everywhere, right? So, but in the Gaussian case, what you do is that you just replace it with the fractional power. So yeah, the constant alpha is called the parameter of the stability, and you sort of see why, because if you sum up Gaussian and if you sum up Cauchy distribution, the property wouldn't be preserved because you will be summing up distributions which have different shapes. But if you sum up distributions coming with the same stability property, which means that the decay of the tails really is the same, the property is being preserved. There might be some of you who enjoy physics and who enjoy working with Markov processes and who might like Markov chains or whatever. So this slide is just to sort of make the point that the stability property is basically preserved even if you want to work with Markov processes. So if you go from Gaussian distribution to the Brownian motion, you can go from Cauchy distribution to the Cauchy motion, and the stability property, the scaling property, the nice scaling property which you have in the Brownian motion, it is going to be preserved even in the case when you relax the assumption that the distribution has to be Gaussian, but it can be anything other coming stable. Okay, so yeah, I'm very sorry, but we are there back again with the characteristic functions. Now, this is a very general characteristic functions. I think mathematicians like this thing which is called Levy processes. So this particular measure in the integral wouldn't have to have this form. It can have other forms, and it would generate a different type of processes. But over here is a sort of diffusion part, and over here this is telling you if you will be having a stochastic process. This is basically going to tell you about with which intensity the jumps are occurring. So if you have a Gaussian distribution, there is loads of tiny little jumps. If you have a Cauchy flights, you will see that there will be happening big jumps, and there might be few very small increments, but then you will be having these big jumps. So something like those of you who work in finance, it's probably Cauchy distribution wouldn't be probably the best choice of the model, but it would be having a bit more realistic maybe shape. The important thing here is that particularly for the stable law, you just can't mix Gaussian and something different than Gaussian, so Cauchy, and expect that you are going to keep the stability property, which is basically something which you have seen in the definition, but you can prove it too. Anyway, why this is important is because if you work out the integral, you will get to that particular thing where things starts to get awkward. And maybe when you will look into the Wikipedia and you will be looking into the definition of the stable laws, you will find that page, and that will show you that the stable law is defined like this, with this characteristic exponent. And this is a sort of place where loads of comedy of the mistakes starts. Because when you look over here, when we were working out that integral, the integral on its own would be continuous in the parameter alpha, in the parameter beta, and in the other gamma and lambda. But because these functions, when we work out the integral, they would be nicely continuous. But then we do some kind of awkward algebraic manipulations just to have this user-friendly form which people can nicely associate with, and which in a certain way is pretty helpful. But what had happened was that we introduced a discontinuity, and it comes with a price. So just to quickly summarize, over here in the kernel, we have to sort of specify if we have alpha equal 1. So these would be basically the cases when the Cauchy distribution, where you would consider the asymmetric cases of the Cauchy distribution. The parameter beta is very nice and user-friendly because it controls the asymmetry. And you know that anything which has a beta equal to -1 is going to have majority of the probability mass located on the left side of the real line, and majority of the probability mass will be located on the right side for case when beta is close to 1 or equal 1. Lambda is very simple scaling parameter, and the other guy is just shifts the things. So I think before I move to more details or where the things get tricky, I will sort of show you what type of distributions I have been speaking about the whole time. So this is a case when alpha is 1.97. So you might have a feeling that this is pretty much like a well-behaved Gaussian distribution. And you see that when beta, so here's our beta is -1, here is beta 1. So you see that the way how you can shift the probability distribution, you don't have so much opportunity to shift the probability mass. So basically the closer you are getting to Gaussian distribution, the less flexibility you have to move with the distribution. But let's consider other examples. So this is when we would be having alpha 1.9. So things starts to get a bit more open. And here you start to have a bit more flexibility. So I have to admit that when I used to work with the financial time series, I was sort of always playing with the data between region 1.7 to somewhere around 1.85, 90, depending on the type of the indices or on the type of the data. And of course, you might not be very happy for the fact that this distribution doesn't have a second finite moment. So usually just the exponential truncation for the tails a little bit helps. Yeah, you have there the flexibility, and the 1.7 is quite reasonable. But okay. Usually it's more fun when you sort of tend down to 1 because the distribution starts to be real fun. So for 1.5 you see that you can really start to shift the probability mass. This is the case for 1.3. And this is 1.1. Yeah, and then I'm very sorry. I don't have pictures for below 1. But what happens for the case for below 1 is that so in case when the lambda is between 1 and 2, the probability distribution is centered on the real line. But when the alpha becomes smaller than 1, in the extreme cases, the probability distribution will be located only on one semi-axis, and in the second, or in one of the semi-axis. So sometimes when you like to work with, when you like to subordinate the Gaussian distribution, so this is very helpful thing which you can use, because if you have the extreme distribution located only on the positive part of the probability mass, you can very easily model the time, because sometimes we don't like when the time flows backwards in our models, and it can also flow forwards, but over here it can flow only forwards when it's located. That was actually one of the models which Mandelbrot was using for modeling time series. I think it's Mandelbrot-Taylor model, something like 1965. And he wasn't actually modeling the time, but he was modeling the volume of the market, I have a feeling. So he subordinated the Gaussian distribution with the alpha stable located on the positive part. Okay, so what are the numerical issues which we might be facing? The numerical issues are basically that the distributions are not converging. If we take parameters alpha and beta and gamma, they won't be converging in this case to the alpha, which is going to be equal to 1. It will actually converge to the probability measure, which will explode. So this is a big source of the numerical inefficiencies. So whenever you would be working with the stable loss, and you would be like to work in the regions which are close to 1, there will be just your numerical methods will tend to break. So it's very good to look for these regions. There is other parameterization, which is a sort of a help, and this parameterization is it just corrects the drift. And if you correct, if you little bit shift the mass, the location, what happens is that at least you will get the discontinuity gets actually corrected. But it comes with the price, because if you look at the drift, at the shift which we had to do here, we basically have to shift the parameter alpha. So as we are changing alpha, we also have to be moving the probability mass. So it doesn't give you any sort of nice statistical properties, but it is helpful for deriving numerical methods. So this would be the transformation equations which you would be having. And yeah, so this is where it becomes important, because when you think about alpha getting close to 1, you really will be shifting the distributions quite a lot in this parameterization. So the forms of the stable densities, we know them in the closed form for the Gaussian distribution, Cauchy and Levy, as I was saying at the beginning. But the life isn't so bad, because there are integral representations which are quite good to implement, and I was pretty much working with majority of these implementations. You can approximate them via series expansions. They work very well in the far regions or in the core regions, but all the things between is just yeah, I mean, it's asymptotic series, so they won't be really approximating it in the regions for which they haven't been derived. Fast Fourier transform has issues, especially if you are working in the region which is below, for alpha below 1, because you need loads of points, and you will have problems with stability, especially if the alpha is becoming smaller. The Gibbs effect will really kick on, and the tails will be oscillating, so the Fourier transform, fast Fourier transform won't be working really well. This is other parameterization which is pretty helpful for deriving all these integrals and all these sums which I was talking about. And well, I would like to give you a list of references which I think are quite important, especially when it comes to the numerical implementations. So I think I can highly recommend just this old textbook, where are all mathematical proofs and all derivations to pretty much start with. This is a very good library, and I have to say that I am a great fan of the library, and hopefully, I mean, fingers crossed that there will be wrappers implemented around it, and it will be used in the SciPy, because that would be the best. There is there is like a parallel computation for the integrals, so it's nicely speed up. And I think that yeah, if you are fans of C, C++, it's definitely a library to look into. I would be very careful about this particular paper, and this is quite funny, because basically this library is built on this paper, and many implementations of the stable laws are built on this paper, but I think you need to test your methods if you are using this paper. So basically, any library which you will be using, just test your methods. And actually, I can highly recommend for unit tests tables and graphs in this particular old paper, because I think that over here I can pretty much associate with the numbers which are over here. And if you will be testing it, you will realize that it is different numbers than which you have in this paper and which you have in all those libraries. So you can actually maybe figure out how the errors are propagating through the numerical software. So the tips, this is the last slide, right? So the tips for the numerical implementations when you would try to maybe play with these distributions. So because of all these different parameterizations, firstly, just really pick up which of the parameterization it is, because often people are thinking like this is this parameterization, so it's going to be these parameters. But there are these transformation equations, and you will realize that just scaling constant or location constants, they can really make quite a big difference in the papers. There is just like loads of errors in the papers propagating just due to this fact. Test the implementation, and this is like if you just generated random samples, and you will compute the histogram, and you will test your numerical implementation of the density against these estimated histograms. You will like sort of see what I have been trying to suggest here. The other tricky bit here is that the majority of the tests, of the unit tests in the software, are carried for the basic parameters, because I mean you are writing unit tests, so what are you going to write? Let's pick up the nice numbers, right? But the trick comes where the numerical formulas are starting to break, so it is really good to test exactly for these problematic regions, and like really just take the as fine granularity as you can, and different sort of numerical implementations. And yeah, you use different methods, and definitely try to use this paper. And well, good luck, because I think it's pretty much versatile distributions to play with.
Andrea, thank you very much.
Welcome.
We have time for one question.
And then we'll move on to the news that was slightly wobbly earlier. I've got a question. Andrea, how much, you talked about adding this work to SciPy. How much of that work that was added was your work?
So there is a big chunk of the code which we've added on the GitHub, and shamefully, I think that a big chunk of this work actually haven't been pushed through because there was some competitive part. Yeah, that's why I'm saying like I'm not really happy about the numerical methods which are being used there, and it really needs revision. And that's why I'm talking about it. Just learn how to work with the distributions and sort of learn how to correct it, because it is a big shame that they are not being used. There are people like Mandelbrot or Paul Levy who played with them and who spent all their lives on trying to work with them. So just, yeah, don't be stuck in Gaussian distribution and all the basic things. There's lots of nice scientific papers to generate out of that.
And crucially, when you talk about using it and being wary of what's there, you talk about unit tests. Brilliant.
Yeah.
Talk about testing the code and not just using it blindly, which of course is terribly sensible. And we all write unit tests because we're all very good engineers. We'll move on to the news now, I think. We're going to give a double round of applause to Andrea because not only is she presenting something, but also she's contributing to our ecosystem.